Hello, we're here to talk today about auralization processes at Arup. My name's Shane Myrbeck, and I'm an associate principal in the Los Angeles office.
And my name is Willette, and I'm a consultant in the Seattle office.
So a big part of the reason that we're here talking about this in any respect is because of our sound lab. So we've run an auralization studio at Arup for over 25 years now, which is the sound lab. We have these in offices all over the world. There are over 30 of them now, and they all have different features and different loudspeaker setups and things like that. But the primary purpose of them and the origin story of them is for a dedicated purpose-built auralization studio. Over the years, they've evolved beyond just that. So there's the sound lab, which is primarily dedicated to auralization specifically. But there's also an experience lab, which kind of expands beyond sound to XR video and to even some haptic and olfactory elements in some cases. And then we have our M lab, which is the more portable version of the sound lab, which could exist on a project site or in a conference context or something like that. Key to all of these rooms is flexibility of software platforms. For the Sound Lab specifically, we tend to group things in three categories. We have the recording aspect, so we have a 3D recording process that we can play back and modify in some way to show design or various biophilic soundscaping concepts or music recordings. We have our modeling process, which is what we're going to talk about most today. The computer modeling process. And then we also use the platforms as a composition studio and for exhibit design because it's a 3D sound canvas. But all that to say that we need to use many different software packages to accommodate all these different use cases. And some of the projects that we do in there also span quite a variety of sectors. So these are half a dozen examples amongst hundreds of different projects we've auralized in the Sound Lab, from a reverberation chamber for a tour for Bjork, to museums such as the Paralympic and Olympic Museum in the US and Rafik Anadol's Dataland, to transit centers. This is the 2nd Avenue subway in New York, but we've also done high-speed trains in the UK and elsewhere. So it's a wide variety of projects, again, needing a kind of a lot of flexibility within the auralization studio itself. And one thing we're always looking for within the Sound Lab context is efficiency. So because we're using so many different platforms and so many different techniques, there's often a bottleneck somewhere in the process. So one thing that we've focused on over the past couple of years is trying to gain efficiency in our traditional process, which was taking a sophisticated BIM model or 3D architectural model and kind of modifying that 3D geometry to get into a traditional geometric acoustics software package, then taking the output of that and putting that in something like Max MSP to get the multi-channel output into the Sound Lab. One of the things that we love about the Treble software package is that it adds a lot of efficiency into that process. So I'm going to hand it over to Aaron now to talk about a few project examples that describe that.
All right, so I'm going to talk through a few case studies where we've been able to use Treble on projects recently, and this has been for both numerical modeling and auralization. So the first one that I'll discuss is the Perception Engineering Lab at the Salford University in the UK. And this is going to be a new ITU standard listening room where they want to do very precise analysis of how spatialization affects perception of sound. And so they're building this room to accommodate at least 50, potentially up to 120 different loudspeakers to do a really higher order ambisonic listening format. And we've been able to use Treble so far in just the early stages of the project where we are to track some early reflections throughout the space. So as I mentioned, there are going to be a lot of loudspeakers in this room, and because they want to be so precise about spatialization, you need to be really careful about early reflections blurring the image or shifting the image between locations that aren't exactly what you're trying to model. And so we've been following the standard guidance of tracking any reflections that are within 15 milliseconds of the direct sound and making sure that none of them reach within 10 dB of that direct sound. And so using Treble's reflection tracker, it's been really easy to kind of visualize exactly where all of these speakers are and where those first reflections are coming from. And we identified one, for instance, from a door that didn't have absorption in the initial design. We found some problematic reflections there, and now we can make the case for it. And this isn't brand new technology, but Treble's interface is so well organized and streamlined that it's easy to keep track of a really complicated system like this and track all of the potentially problematic reflections through the space. Okay, so next I'm going to talk about the project which we can see a little piece of here. This is an indoor sports practice stadium. And what you're seeing here is a piece of the ceiling geometry, which has this complicated lattice. That's these structural beams that extend about 6 feet or 2 meters deep. And they're flush against the roof, which is this complex, multidimensional curved shape. And the room itself is also quite a large volume, about 300,000 cubic meters on that order. So as you can imagine, this is a pretty tough problem for most room acoustic solvers to handle. So specifically what was so tough about this one is just modeling this complex geometry in a large space in a way that won't, make the software freak out and take a million years to process your data. So the architectural model we received with that complex geometry had a lot of little gaps and holes everywhere, which we all know usually acoustic solver software doesn't like. But to model it really precisely in a completely airtight fashion with those lattice beams being flush against the roof in every location was an extremely time-consuming process. And so what we did instead is we took something more similar to the architectural model, where that lattice was floating just like a couple millimeters between the actual roof itself. And Treble accepted this geometry without really any complaints. And one of our more standard ray tracing software packages would accept the geometry, but would take about 42 days to produce results, which pretty tough to work with that. So Treble would run those same results in less than an hour. And so then we could run through all of our design conditions, get our numerical results, and eventually we were able to produce a really compelling auralization of some of the graphs that you see there, which are the reverberation time in the space if you don't have any absorption in the ceiling, or if you do, which in a huge volume space like this is so important. And so we were able to communicate that in our auralization, all reach a decision with the client, and it was a great success. Another interesting auralization that we've worked on was this event center presentation stage. And as you can see here, there are these architectural features on either side of the stage, which they were calling fins. And in the initial design, we noticed that these fins were basically just parallel flat surfaces perpendicular to the stage. And as a result, we noticed that there might be a problematic flutter echo between these. And that's a really difficult phenomenon to explain to a non-technical audience, and so we decided that auralization was probably the best path forward. So we threw together a quick treble model, put it in the binaural auralizer, and we could immediately hear the problem. So then we could propose some potential solutions, like either putting absorption on the faces of the fins or just rotating them upstage so that they aren't parallel to each other. And we presented this auralization both in person in our sound lab and remotely.
And this is one of the major breakthroughs in terms of using the platform at Treble for its user interface. So for a long time, and this was exacerbated during lockdown when everyone was remote, we've developed various ways to do distributed team presentations. And sometimes, in years past, that ended up being just a fixed video that we would send off to people. But the hybrid presentation of being able to do ambisonics in the sound lab with binaural at home has been somewhat elusive. So in this case, what we had was members of the project team in the sound lab in San Francisco, some of the project managers and a few of the technical folks on the project. But then we had 4 people remote, and they were all of varying levels of technical expertise. So we had the audio engineer for the space, who is the highest level of technical expertise. Then we had the set designer, I would say the next tier, and then a person from Arup, and then we had the project executive from the client side, who had kind of no level of technical expertise within the context of what we were presenting. We were able to present the material in the sound lab with us running the interface and give instructions to all the people that were remote and have them navigate the web browser interface. everyone went offline and listened for a few moments, and then came back online, and we're all able to agree on the direction for the project within a few minutes. So in terms of a presentation interface, it was a step change in what we were able to do. One modeling technique that we've developed over a number of years, over a decade now, is this concept of acoustic wayfinding. So the gentleman pictured in the photo here is an architect named Chris Downey. He was a practicing architect for 15 or so years, and then had a surgery on his brain that caused him to lose his sight unexpectedly. So since then, he's developed an architecture practice called Architecture for the Blind, where he uses acoustic wayfinding as one concept within a framework of universal design. So we've worked with him over the years to be able to try to model these concepts of acoustic wayfinding in the design phase to get buy-in from various stakeholders on projects to implement them on the projects that Chris is working on. So the tools of acoustics wayfinding is that you have your palette of acoustic materials, and this is something that's obviously known through the history of acoustic consulting. So you have your absorption coefficients, scattering coefficients, and project experience to be able to select various materials to create these acoustic moments that could provide some directionality and wayfinding elements. You need to take those materials and then develop an intuitive sense of spatial transitions. So, for example, the transition from cane taps on a concrete surface to a carpeted surface, transitions from a reverberant, corridor space to a more absorptive space. Asymmetry within spaces that can be learned. So, for example, absorption on one side and reflective surfaces on another side that you can kind of understand over the time that you experience the space and use that for navigation. All these are various things you can implement in a project that help with acoustic wayfinding. During the design phase, of course, the modeling of that is something that we've been able to do for a long time in terms of the different materials and the changes to those materials. But one really important piece that's been elusive over the years is the dynamic modeling aspect of this. So ideally, we'd be able to navigate through each of these spaces with these acoustic changes, and then be able to select the different navigational tools that worked best for a given client. So in the past, what we've done is kind of stitched together various software packages to make this happen. And it's been successful, but it's a very laborious process of using different packages for different elements of this dynamic modeling to get, to be able to express the design changes that we're trying to communicate. Over the past couple of years, in the last two projects we've worked on with Chris, we have been able to develop a new method for dynamic modeling that's been much more successful. And I'll hand it back to Aaron to discuss some of the specifics.
Yeah, so the first project that I'll talk about with this is Guide Dogs for the Blind, their new campus in Oregon. And this is a training facility for guide dogs for the blind, and as well as an education and kind of residential place for these people to go while they're being paired and getting to know a guide dog. And this is one of the buildings that we've studied a few times where you've got a really long hallway that's kind of acoustically homogeneous, and you're worried about people trying to navigate through this hallway not being able to really track their progress through it. And so we can use acoustic wayfinding for this by varying the finishes along the wall, like Shane was talking about, and also varying the shaping of the wall itself. And so for guide dogs, we use Treble's Auralizer the whole way through, and we simulated the dynamic walkthrough element of it by crossfading between different listening positions. And the main kind of win here is that we were able to really quickly iterate on designs and take direct output from Treble's Auralizer, recorded into our computer, and then easily crossfading between those to get our sort of simulated dynamic walkthrough. And this was presented to the clients in our sound lab in San Francisco, and it was very effective. So then for the next project, where we had a really similar problem come up, this is the Indiana School for the Blind and Visually Impaired. They're designing a whole new education building. And they also had a long hallway where they were worried about students tracking their progress along. And so we proposed some similar ideas where you can have areas of absorption flanked by areas of reflection, and kind of trying those out in different spots in the hallway. And for this, we used one of our other modeling tools in conjunction with Treble. And so our other modeling tool is an acoustic solver for the Unreal Engine, which is used for video game production, as well as a lot of different architectural disciplines, visualization, data management, so on and so forth. And the benefits of using Unreal Engine and the acoustic solver for it is that you can do true dynamic walkthroughs. You can use an Xbox controller, or you can kind of preset your trajectory that you can play back for the client, and you'll walk through the space and you can see it as it's happening, and it's great. The main downside is that the acoustic solver plugins for Unreal Engine aren't usually targeted at our industry, and they don't usually achieve quite the level of accuracy that we look for. And so here we were able to use Treble to validate and calibrate what we were getting out of Unreal Engine. We could make the same model in Treble in an Unreal, see if we were hearing the same thing out of it. If we weren't, the Unreal plugins have some design controls that you can manually mess with to try to change the dry-wet ratio, change the reverberation time multiplier as a whole. And so we could dial that into exactly perceptually match what we were getting out of Treble, which for an early design level auralization is absolutely sufficient. And the pros of using that dynamic walkthrough auralization technique were really, really compelling to the client. Again, they came into our sound lab. We had Chris Downey come in there as well, and he was really happy. The clients were really happy with the differences they could hear with the different design conditions walking through this hallway.
Thanks for watching. Once again, Aaron and Shane from Arup. If you'd like to contact us, our contact info is available. And
yeah, and thank you so much to the Treble team for putting this all together and for working with us on a great collaborative relationship on some of these features for their platform. It's been a pleasure. And thanks as well to Acoustics for presenting next.